This video is about Physics 301, Module 6, covering work, energy, and power. It is based on Chapter 6 of Algebra-Based College Physics 1 by Moses and Tom. Energy is defined as the ability of a body or system to perform work. In nature, energy can be transformed from one form to another. A system refers to an aggregate of two or more particles treated as a single unit. There are several types of energy, including mechanical, heat, electrical, chemical, and atomic energy. Each plays a crucial role in various physical processes. Work done by a constant force is calculated as the product of the force component in the direction of motion and the distance moved. It's measured in joules, where 1 joule equals 1 Newton meter. This diagram illustrates the work done when a force is applied at an angle to an object's displacement. The formula W equals Fdcosθ theta accounts for the angle between the force and displacement vectors. When there is no displacement, or the force is perpendicular to the displacement, the work done is zero. Here, with zero displacement, the work is zero. If the force is perpendicular to the direction of displacement, meaning an angle of 90 degrees, then cos 90 degrees is zero, resulting in zero work done. Positive work occurs when the force and displacement are in the same direction, with an angle of 0 degrees. Since cos 0 degrees is 1, the work done is simply Fd. Negative work occurs when the force and displacement are in opposite directions, at an angle of 180 degrees. Since cos 180 degrees is -1, the work done is negative Fd. For a non-constant force, the work done on a system is determined by the area under the force versus displacement curve. This method allows us to calculate work even when the force varies. Here's an example of calculating work done by a non-constant force. The work is found by calculating the areas of the triangles formed under the force displacement curve. Now let's consider an exercise to apply what we've learned about work done by non-constant forces. You'll need to calculate the work done from x equals 0 to x equals 10.0 meters. To solve this exercise, divide the area under the curve into a triangle and a rectangle. Calculate the area of each shape and sum them to find the total work done. Example 6.1 asks us to calculate the work done pushing a lawnmower. We'll use a constant force, an angle, and a distance, then convert the work to kilocalories. The solution involves substituting the given values into the work formula. The result in joules is then converted into kilocalories for comparison. Section 6.2 introduces kinetic energy and the Work-Energy Theorem. This theorem states that the net work on a system equals the change in its kinetic energy. Gravitational potential energy is explored in Section 6.3. Work done against gravity becomes potential energy, and as an object descends, this converts into kinetic energy. Section 6.4 covers rotational kinetic energy. For an object with a moment of inertia I and an angular velocity omega, its rotational kinetic energy is given by the formula shown. Conservative forces, discussed in Section 6.5, are those where work depends only on the start and end points, like gravity or spring force. Mechanical energy is conserved with these forces. Non-conservative forces, such as friction, are introduced in Section 6.6. For these forces, the work done depends on the path taken, and they can change mechanical energy into other forms, like thermal energy. Section 6.7 focuses on the conservation of energy. Energy cannot be created or destroyed, only transformed or transferred. The equation shown describes this when both conservative and non-conservative forces are present. Power, as discussed in Section 6.8, is the rate at which work is done. It is calculated as work divided by time and is measured in watts or sometimes in horsepower, where 1 horsepower equals 746 watts. This slide reiterates the definition of power as the rate at which work is done. We will now look at some end-of-chapter problems from Perusol to apply these concepts. Problem number 27 asks us to calculate the work done by a supermarket attendant pushing a can of soup. We need to express the answer in both joules and kilocalories. To solve problem number 27, use the work formula for a constant force. The force and displacement are horizontal, so the angle is 0. Then convert the result to kilocalories. Problem number 29 involves an elevator car. We'll calculate the work done by the cable, the gravitational force, and the total work done on the elevator. For part A of problem number 29, we analyze the forces acting on the elevator using a free body diagram to find the work done by the cable, considering friction. For part B, we determine the work done by gravity. Then for part C, we find the total work done on the lift by summing all the individual works.